Dear friends, there are not too many of us sitting right here, but I'm sure that everybody will watch this video. So a special hello to these listeners. I'm glad to introduce Pieter Senden from KU Leuven, and today he will speak about right-angled Artin groups and dictionary between graph and group. So Peter, you're welcome.
So thank you, Timur, for the introduction. Also, thank you, Timur and Alina, for the invitation to give this mini course. So today, I will give the first of two lectures regarding right-angled Artin groups. Today, it's more aimed at a more general audience in the sense that I will give examples of how algebraic properties of the right-angled Artin group translate to the graph theoretical properties of its associated graph and vice versa. With in mind that it can be interesting for people that start working with right-angled Artin groups to have sort of an overview which properties are known. And on the other hand, for people that are familiar with right-angled Artin groups, perhaps see the results presented in a different way, or in the second part, see the known results applied on a topic they may not be familiar with. So wait, let me start with the definition. So I give examples later, but to give it in perspective, it's useful to start directly with the definition. So we start with the definition of a graph, and in my talk and the next one, all graphs will be both finite and simplicial. So it means that I only have a finite number of vertices, and there are no multiple edges or loops in my graph. So I define a graph as a pair of V and E. So V is a set of vertices, and E is a set of edges. And I view E as a subset of all subsets of V containing exactly two elements, this in shorthand notation. And I will denote every graph in this format. So the letter of the graph gamma, and then its vertex set and its edge set. And if I modify gamma in a certain way, for instance, write an apostrophe, I will denote the same apostrophe with V and E to denote that this is the corresponding vertex set. And for edges, I won't write them as sets, but I will simply write them as a tuple or a concatenation of two vertices. So either VW is an edge in E or it's not an edge in E. I will write it as follows, just to have the notation clear from the beginning. And then with this, we can define quite easily the right-angled Artin group. So starting from a graph gamma with vertex set V and edge E, we associate it with the group. It has the following presentation. So it's generated by the set of vertices, and the only relations you add to your group are commutator relations. So which vertices do you let commute? Only those that are connected by an edge. So for instance, to give an example, if you take all graphs on three vertices, there are four possibilities. Either none of the vertices are connected, so you don't have any edges, so you don't have any commuting relations or relations at all. So you just take a free group generated by three vertices. So the RAAG, or the right-angled Artin group associated to this graph, is just a free group on three vertices. On the other hand, if you just take the complete graph or the clique on three vertices, then by the definition, everything commutes. And this is the only relation we add. So we have three generators and everything commutes. So this gives us a free abelian group. And then in between, we have two other possibilities. The first case, we have that only two vertices commute, and the third one doesn't commute with either of the two initial ones. So this part of the graph will generate a free abelian group of rank 2, and the other sole vertex will generate a free abelian group of rank 1. And then together they will give a free product, since there are no relations among the vertices on the left-hand side and the one on the right-hand side. And then as a final case, we have this one. So we have two edges. So the two vertices below will generate a free group, and these two vertices commute with the third one. So we will get another free abelian group and then a direct product among them. So in this way, we might suspect that we don't get any new groups, but it's not the case. If you take, for instance, a regular pentagon as graph, then the associated right-angled Artin group does not have a nice description in this way. So it's really a new type of group we get using the definition. Now, to give some historical background, right-angled Artin groups, or RAAGs for short, are denoted with several other names or can be seen as subfamilies of other families of groups. If you look into literature, there are results that are proven for right-angled Artin groups, but not given the name right-angled Artin groups. And I've given some examples of this. So one of them is the name partially commutative groups. And this name comes from the fact that, as we saw before, in some sense, right-angled Artin groups interpolate between the free group and the free abelian group in terms of commutativity. The free group, nothing commutes, and free abelian group, everything commutes. And right-angled Artin groups are somewhere in the middle. Some things commute, some things don't, hence the name partially commutative groups. Another way they are known are as graph groups. Really, this name, they're called the graph groups. And I think the name comes from the fact that these groups are naturally defined based on a graph. Now, of course, it depends on what you call naturally. If you take the automorphism group of the graph, it's also a natural way to associate a group to a graph. But in terms of presentation, this is the most straightforward way to construct a group based on your graph. Then as subfamilies, you can view them as two types of subfamilies. On the one hand, you can view right-angled Artin groups as graph products. So generalize the idea of taking a graph and associated to it a group using this construction. So instead of just taking a vertex for each or a generator for each vertex, you take a group for each vertex. And then to construct a graph product of these groups with this information, you first take the free product of all the groups, and then in analogy with the right-angled Artin groups, you let two groups in this free product commute, if and only if the corresponding vertices are connected by an edge. So if you take then for each group GV a free abelian or a rank 1 free abelian group, so the infinite cyclic group, then you will end up again with the definition of a right-angled Artin group. So RAAGs are graph products where each group on the vertex is an infinite cyclic group. Another way right-angled Artin groups fit into a subfamily of groups is for the family of Artin groups or Artin-Tits groups. This generalizes the construction of a right-angled Artin group in a different way. So instead of taking other groups on the vertices, we take another type of graph. We start namely with a labeled graph. So again, the same definition, finite set of vertices and a set of edges, but each edge carries a label, which is denoted by MVW, and all the labels have to be positive integers, at least 2, but they also can be equal to infinity. So we can give the edges a label infinity. And then using this labeled graph, we can construct an Artin group with the following presentation. Hopefully the thing goes away. So you take as generating set just V, and as relations, you take alternating words in the letters V and W, starting with V, and the number of letters you use is equal to the label of the edge you were using if the edge label is not infinite. So you see here, you take MV, and sorry for the black piece, this wasn't the plan. So you alternate V and W, MVW times, and this word equals the same word when you alternate between W and V. So you swap the beginning letter, but you do the same, you tick the same amount of letters. Now, for a right-angled Artin group, each label is either 2 or infinity, because if you just take 2 letters, then the relation states VW equals WV, which is precisely the commuting relation we started with. Okay, so in this way, right-angled Artin groups occur in different contexts and in different situations and in different forms, but they all speak of the same type of group. Okay, now perhaps some word regarding the terminology right-angled Artin groups. So the Artin groups I already explained. These are groups given by this presentation. But for the right-angled part, we have to go to a family associated to the Artin groups, namely the Coxeter groups. So the Coxeter groups are defined very similarly as the Artin groups. You start with a labeled graph. The group or the Coxeter group associated with the graph is the group generated by all vertices V, with the same relations as for the Artin groups, but with an additional relation, namely that every vertex has order 2. So your group is in fact generated by involutions. So every Coxeter group is a quotient of the corresponding Artin group. And this type of groups, these Coxeter groups, give us an explanation for the terminology right-angled, because every Coxeter group can be realized in a geometrical way as a group of transformations on a vector space where each generator corresponds to a reflection around a hyperplane. So reflection just means the hyperplane is fixed and there is one vector that is mapped to its negative. And for most cases, you can even find a norm on this, or an inner product. This is non-degenerate. And with respect to this inner product, if your relating number MVW is equal to 2, then the corresponding hyperplanes will be orthogonal with respect to this inner product. So orthogonal, or the angle between them is right, or 90 degrees. So this explains the name right-angled Artin groups, because for Coxeter groups corresponding to just a graph with labels 2 and infinity, all hyperplanes that are not, well, all hyperplanes will be orthogonal to one another if they are connected by an edge. So this explains why we speak of right-angled Artin groups in this specific case. Okay, with the etymology and the context behind us, we can go to the main point of the talk. So as I said in the beginning, the goal of the talk is to give or to discuss results that translate graph theoretical properties into group theoretical properties and vice versa. So maybe characterizations of certain group theoretical properties in terms of the graph. What I won't be mentioning, or well, almost not be mentioning, are results that are graph independent. For instance, you can prove that all right-angled Artin groups are linear, that they are all torsion free, but these are properties that do not depend on the graph, in the sense that it's just a statement for every graph, the group is torsion free. So there is no relation between the graph and the group that it's truly dependent on the graph. And I say almost because there will be some that can fall into this category, but more on that later on. And in the aim of the second talk, I've marked certain results with an asterisk to indicate that I will use them either explicitly or implicitly in the second talk, just for people that want to take notes and want to know what will be useful later on, that they can indicate them at the moment. Okay, so what will we discuss? We will see, okay, for groups, what can we talk about? For instance, isomorphisms of groups, subgroups, quotients, factorizations, and other algebraic properties, and see how they relate to the graph. But first, I need some more definitions. And as I mentioned as I stated in the description of the course on the website, I tried to make some pictures to illustrate things. So here, the pictures continue. So given a subset V prime of vertices, then with gamma of V prime, we mean the full induced subgraph on V prime. So what we mean is gamma V prime is a graph with vertex sets equal to V prime. And the edge sets of this induced graph are all edges of the original graph that connect two vertices in V prime. The full graph is a composition of two pentagons connected in this way. And if you take for V prime the set of blue vertices, then the induced subgraph is the blue pentagon. So any edge of the original graph connecting two vertices of the blue set is contained in this induced subgraph. Okay, this is the induced subgraph definition. And then for on the right-hand side, we define the link and the star of a vertex. So the link of a vertex consists of all other vertices that are connected to this. So for instance, the link of the blue vertex is the red vertex, are the three red vertices. And the star of a vertex is simply the link together with the vertex itself. Hence the name star, because you get some sort of star shape. So in this case, the star of the blue vertex are the 4 vertices here. Okay, these definitions will come and go at some point, so I wanted to say them in the beginning. Okay, so as I said, we will look at group theoretical properties and see how they translate into graph properties and vice versa. And the first thing you can ask is, well, you have this notion of taking a graph and forming a group with it. Of course, if graphs are isomorphic, then the groups we define with them will also be isomorphic. But does the converse hold as well? In the sense that for any 2 different graphs, do we get different right-angled Artin groups? And the answer is yes. Karel Droms proved in the late 80s that 2 right-angled Artin groups are isomorphic, if and only if their defining graphs are isomorphic. So one direction is trivial from right to left. The other one from left to right is not trivial. But we see that all information from the graph is retained when we go to the group, because up to isomorphism, if 2 graphs are not isomorphic, then the groups won't be isomorphic as well. So this is already a first indication that right-angled Artin groups will behave more or less nicely, since there is no information lost by going to the right-angled Artin group, or at least not on this level. Okay, now this is one type of isomorphisms we can look at, but we can also look at what happens if we do a group theoretical construction or a graph theoretical construction and see what happens on the other side. So on the level of graph, if you have 2 graphs, gamma 1 and gamma 2, you can construct new graphs using these 2 in the following 2 ways. So you can either define the simplicial join, which we denote by a star. So gamma 1 star gamma 2 is the graph with vertex set, the disjoint union of the 2 vertex sets of gamma 1 and gamma 2. And as edge set, we take all edges of gamma 1, all edges of gamma 2, and all edges connecting one vertex of gamma 1 with one vertex of gamma 2. Okay, and another construction is a disjoint union, where we just view the 2 graphs together as one, but we don't add any edges. So to illustrate this, here we have a simplicial join. So we take 4 red vertices, which is a co-clique, so a graph without any edges. And we take the simplicial join with a graph on 5 vertices with no edges, and we get this full graph as a simplicial join. And then here as a disjoint union, well, you just take a triangle and an hexagon, you put them together and you get a new graph. So we view this graph as one, not as 2 individual graphs, but just one graph. Now, this is a construction on graph theoretical level. And how does it translate to groups? Well, you can see it quite directly from the definition of a right-angled Artin group, that if you take a simplicial join of graphs, then the associated right-angled Artin group will be the direct product of the corresponding right-angled Artin groups. So here, well, we have a RAAG associated to the blue ones and one to the red ones. What do we do on the level of groups? We let everything in the red group commute with everything in the blue group. So this means that we take the direct product of them. And similarly, if you take the disjoint union on the level of groups, this just means the free product. So you just take 2 groups and let them generate a whole new group, but you don't impose any additional relations between the 2 groups we started with. So this corresponds to taking the free product of them. And I know that there is a bit of a oddity with notation. So here the star on group level is a free product, whereas the star on graph level is a simplicial join. So this is a bit unlucky that they use the same symbol for different notations or for different meanings, but I hope this will be clear throughout the presentation that there are not that many confusions about this. Okay, so based on, why doesn't he want to go to the next slide? Oh, this is, damn. Okay, I have some problems with the, why doesn't he, okay, now he goes, okay, I have to scroll back. Hey. Okay, I'll just do it with my mouse now. Okay, right, so we've done isomorphisms. Most we can do, we have isomorphisms on the level of graphs, translated to isomorphisms at the level of groups and vice versa. And now, next to isomorphisms, another thing that's often done in groups is look at subgroups. So given a graph, there is a natural way to go to the subconstruction, the subgraph just taking the induced subgraph, as I explained in the beginning. And then on the level of groups, you can look at the subgroup generated by the vertices you chosen. So the subgroup V prime, or the subgroup generated by V prime, yields a subgroup or right-angled Artin group A gamma, but it also has an associated graph, namely the induced subgraph. It would be nice if the right-angled Artin group associated to this subgraph is the same as the subgroup generated by the set of vertices V prime up to isomorphism. And this is indeed the case. If you take a subset of vertices, then the subgroup generated by V prime in the right-angled Artin group you started with is isomorphic to the right-angled Artin group associated to the induced subgraph. Now, I've written here Van der Lek as the one who proved this, but he didn't prove it only for right-angled Artin groups. This is a result that also holds in general for Artin groups. As I mentioned, or as I defined in the beginning, so if you take this more general construction with labeled graphs, the same result holds. If you take a subset of vertices and generate a subgroup, it will yield an Artin group with the defining graph as you would expect. Now, why are we interested in these subgroups? Well, first, for right-angled Artin groups, they are called special subgroups due to the way they are constructed. But for general Artin-Tits groups or Coxeter groups, they are also called standard parabolic groups, just to give the name giving in more generality. So these subgroups can be interesting for two cases. First, to see which subgroups of a right-angled Artin group can occur. And then we have this result by Kambeitz from 2009 that states that your subgroup, your group A gamma, contains a direct product of two free groups of rank 2, if and only if your graph gamma contains an induced square. So there is any induced subgraph that is isomorphic to a square. Now, again, one implication is quite trivial. If you have an induced square, then, well, we have, by the previous result, a group of this type. But the strong property is that the converse also holds. If you find in some way a subgroup of the form free group of rank 2 times free group of rank 2, then your graph must contain a square. This subgroup, this direct product as subgroup can occur in some wild form, but if it occurs in a wild form, it will occur as a natural subgroup, so as a special subgroup, I should say. This is one way where looking at special subgroups can be interesting. Another way is that you can decompose your right-angled Artin group as a direct product of special subgroups. So on the level of graphs, every graph that is finite, I should say, admits a unique maximal decomposition as a simplicial join. So constructing one is just do a greedy algorithm, just try to split every factor in a simplicial join until you can't. This will end because your graph is finite. Proving uniqueness is a bit more involved, but not that difficult. But given this maximal decomposition, translate it into groups and you get a maximal decomposition of your right-angled Artin group as a product of special subgroups. So that gamma splits as a direct product of other right-angled Artin groups. And of course, the same you can do for disjoint unions on the level of groups, which then graphs, which then translates into free products on the level of groups. So we have a nice decomposition, but I should warn you at the moment that I do not state that this is the maximal decomposition as a direct product. It could be a priori that your right-angled Artin group admits other decomposition as a direct product, perhaps not as a direct product of right-angled Artin groups, but in some other complicated way. But more on that later. Okay. Now, why do we use these special subgroups? There is another type of subgroups group theorists and mostly combinatorial group theorists are interested in, namely the subgroups of the type of centralizers. So centralizers of elements, because this can give lots of information, for instance, regarding decompositions as direct products. So Servatius in 89 gave a full description of centralizers of elements of your right-angled Artin group. And the statement is quite long, but I'll guide you through it. So it starts with an element X of your right-angled Artin group A gamma. And he first proved that X is conjugate to an element Y of minimal length. Now, what do we mean by minimal length? Recall that a right-angled Artin group is given by a presentation. We take as generating set vertices, and the only relations are commuting relations. Now, if you see your elements of your right-angled Artin group as words in the set of vertices, then the commuting relation will just mean you can swap adjacent letters that are connected in the graph. So the notion of length you have on words of words on a free group carries down to the notion of length you have on right-angled Artin groups, modulo the fact that certain commutator relations will decrease your length if you work them out. But with the intuitive notion of length of words, you can work here. So he first proved that there is some minimal element with respect to length when you conjugate these elements. And with this minimal length representative of your conjugacy class, you can describe the centralizer of it. What you do is the following. So the word Y uses a certain amount of letters, certain letters. You take the induced subgraph on these letters. So this is the graph gamma tilde. Then the right-angled Artin group A gamma tilde splits as a direct product of special subgroups, as we saw earlier. So you have this decomposition. And then since Y lives in this group, you can write Y as a product Y1 to the power M1 up until YK to the power MK, where each YI lies in A gamma I. So you write it as this, and since it's a direct product, each YI will commute with the other ones. Okay, and then, so you see that in the centralizer, the YIs will be contained in them. Because yeah, Y1 will commute with Y1 itself, of course, and then due to the direct product, will also commute with the other ones. So this is one part of the centralizer. The second part is everything that lies outside of gamma tilde, but still commutes with everything inside gamma tilde. So what this means, you take every vertex in the complement of the vertex set V tilde, such that this vertex V is connected to every vertex in V tilde. This will indeed commute with Y, because if V commutes with every vertex in V tilde, then since Y1 is a word using only these letters, V will commute with all the letters in Y1, so it will commute with Y1, and the same for Y2 up until YK. So this clearly lies in the centralizer, and Servatius then also proved that these are the only elements of your group that commute with Y. So the centralizer of Y in A gamma is exactly equal to this subgroup. Okay. More concretely, if you do it for the smallest elements of your groups, namely the generators, then Servatius' theorem states, well, you have to decompose V as this word Y1 up to YK. Well, here it's quite easy. It's just the word V, a single letter. And then you have to add all vertices different from V that commute with it. So these are all vertices W, such that V is connected to W in your graph. But then you see that this is simply the definition of the group generated by this star of your vertex V. So as you would expect, the only things that commute with the vertex are the words that use only letters that are connected to this given vertex. So again, right-angled Artin groups behave nicely, but the proofs are often a bit more technical and use some work to get the result you like. Okay, so with centralizers, you can prove several things. For instance, determine the center of your group. And let me first give a definition. So given your graph gamma, a vertex V is called social if it's connected to every other vertex. So in other words, if its star is equal to the whole graph. Social because it has a lot of neighbors, hence the name social. And the set of all social vertices is denoted by this curly S. And then using the result for the centralizers of generators, it's easy to see that the center of your group will be generated by the set of all social vertices. So in here, for instance, of the image, you have a hexagon with a central edited vertex that is connected to all other ones. So this red one will be the sole social vertex. So the center of your right-angled Artin groups as Artin group associated to this graph will be the group generated by this single red vertex. Okay. So again, here we see that some algebraic property, namely how are the centralizers or what do they look like, can be somewhat derived from how the graph is built up. And especially here, the center can be read off quite easily from the graph. You just look for all vertices that are connected to everything else, and exactly these will generate your center. Okay. So we've dealt with isomorphisms. We've dealt with some subgroups. And now I will go back to the factorizations I spoke earlier in terms of special subgroups. I said a priori it is possible that your right-angled Artin group splits in an other way. I'll just close this quickly. In an other way as a direct product than as a direct product of right-angled Artin groups. But this is not the case. If your right-angled Artin group splits as a non-trivial direct product, then your graph has to split as a non-trivial join. So the only way your graph can decompose as a direct product is if it decomposes as a direct product of special subgroups. So the maximal decomposition I gave earlier is indeed the maximal decomposition as a direct product. Again, right-angled Artin groups behave quite nicely, but you have to do some work in order to prove it. It uses namely the fact that you have a description of your centralizers in terms of your graph. And the details are, for instance, worked out in Coperda. I did not find the first reference that proved this. So I gave one where it is proved. Because for some reason, this is often stated that it holds, but no one bothered giving a reference. So I had a hard time finding the first one that proved this. I did not find him or her, so I just gave one reference. If one of you can give me the first one that proved it, I'd be happy to know. So this is splitting as a direct product, going to the same notion for free product. We have a similar result, namely your graph splits as a free product if and only if your graph is disconnected. So in other words, if you take two graphs together and see them as one graph, we saw that the resulting right-angled Artin group is a free product. And conversely, if your graph splits as a free, if your group splits as a free product, then your graph must look like at least two other graphs put together. So it has two connected components in your graph. And again, here I gave a reference from which results it will follow. So by Brady and Meyer in 2001. So also based on factorizations in your graph translate very well to factorizations in your group. Okay. Then you have a third type of factorization that is also often used for right-angled Artin groups and more generality for Artin groups is this factorization as free amalgamated product. If you take a graph gamma and two vertices that are not connected by an edge. This does not work for free abelian groups, but for all other right-angled Artin groups, it works. And then you take, so this is our graph gamma. You take then the graph gamma 1, where you delete one vertex, so the red one. The other graph gamma 2 is the same graph, but with V2 deleted instead of the red vertex V1. And then you take the fourth graph, namely gamma prime, which is the graph on all vertices except for V1 and V2. So the common piece of gamma 1 and gamma 2. And then there is a way to find gamma as a group or as a graph based on gamma 1 and gamma 2 glued alongside gamma prime. If you put gamma 1 and gamma 2 over one another, you will get visually gamma, but there is some overlap, namely overlap along gamma prime. And this overlap you just identify with one another. And this translates into group theory in the form of an amalgamated product. So you start with taking just the free product of A gamma 1 and A gamma 2. So see this as a disjoint union. But then you identify all common vertices. So you say that this generator is in fact the same as this generator is the same as this generator, and so on. And this construction, so the free product together with the identification of common vertices, is precisely the free amalgamated product, and this will yield your graph or your group A gamma. So again, some graph construction of gluing translates into a nice gluing operation on the level of groups. Okay, good. So factorizations, also some nice translations between graphs and groups. Now, on a higher level, starting from a graph and a group, you can look at its automorphism group. And it would be nice if you can describe the automorphism group of your group in terms, or to some extent in terms of the automorphism group of your graph and other properties. And there are 4 basic types of automorphisms you can describe in terms of the graph. So first, you can find graph automorphisms. These will translate or induce group automorphisms. So for instance, if you take this graph, and as a graph automorphism, you can just rotate it along 120 degrees. This is a graph automorphism, and this will induce a group automorphism by simply mapping each generator to its image under this graph automorphism. All edge relations will be preserved, so it will be, in fact, a group homomorphism. And the second type are just inversions. You take one single vertex A, you map it to its inverse, and then all the rest is fixed. So everything else is mapped to itself, or all other vertices are mapped to itself. This will also induce an automorphism of your group. The third type is the most complicated. This makes your automorphism group quite complicated. These are the transactions. So transactions choose 2 vertices, the V and W. All the rest is just mapped to itself, including W, but V is mapped to the product of V with W. Now, this won't define an automorphism for every choice of V and W. The condition for this to be an automorphism or even a group homomorphism is that the link of V is contained in the star of W. So in other words, everything that commutes with V must also commute with W. So here in the example, the black vertex, the link of the black vertex is the set of these 2 red vertices. And this is exactly contained in the star of W. So the star is the 3 red together with the blue. So we see that the link of V is contained in the star of W. So this will define a group homomorphism of a right-angled Artin group. And then the fourth type are the partial conjugations. So you take, first you choose a, what's it called again? A vertex B. So for instance, we can take here for B, the vertex W. And then you take a connected component of the complement of the star of your chosen vertex. So if you delete all colored vertices, we get 3 remaining black vertices, which are not connected. So one component of this is just the vertex V. And then what you do for your automorphism, you conjugate every vertex in your component with the chosen vertex W, and all the rest you leave invariant. So it resembles inner automorphisms, but it's just partially conjugating with a generator, hence the name partial conjugations. So this gives 4 types of automorphisms, and it was proven that these 4 types generate your whole automorphism group. So this is the result I was referring to earlier. This is somewhat independent of your graph, in the sense that for every graph, the automorphism group is generated by these 4 basic types, but the kind of basic type automorphisms you get is dependent on the graph. And this was first proved for several subfamilies of graphs by Servatius in '89, but then Lawrence proved it for general right-angled Artin groups that is indeed the case. So this is nice because if you have a generating set for your automorphisms, you can either use this to form like a standard representation of an automorphism if you investigate how the automorphisms of basic type relate to one another, or just as a handy tool to test for certain subsets of automorphisms if they are formed in a specific way. Now, as far as I know, there is no general description of the automorphism group for Artin groups in general, but there are certain other types of Artin groups for which there is a generating set known as well. So for instance, CLTTF Artin groups. So the graph has to be connected of large type and triangle free. Large type means that the labels are big enough, and triangle free, so no induced triangles in your graph. Then you also have a description of the automorphism group, and this is due to John Crisp. And this description will come in handy later because we will look at a certain subgroup generated by 3 of the 4 basic types. Now, this is one way of looking at your automorphism group. Another way is a bit more on a higher level. Namely, I've spoken about the decomposition of your graph as a maximal simplicial join. Now, if you do this in a particular way, so if you group your factors in a particular way, you can find a decomposition as follows. So one factor of your graph is a full subgraph, so a clique. So every vertex is connected to every other vertex. So this is a full subgraph KD. And then the other subgraphs in your simplicial join, you group them together based on isomorphism type. So you take, for instance, K non-isomorphic and non-complete graphs, and you take ij copies of the jth isomorphism type, put them together, take the simplicial join, take the whole simplicial join, and then add some clique to it. Then you can describe the automorphism group of the associated right-angled Artin group A gamma in terms of these factors. And this yields the following decomposition. So I'll start with the latter part. So if you fix J, this Rees product means that the only automorphisms on your graph and on your right-angled Artin group are, first, you can permute the isomorphic copies, and then on each permuted copy, you can apply an automorphism of your group. This is the only thing that can happen on these parts of your right-angled Artin group. There is no mixing of 2 isomorphic copies. So if you have 2, they are either swapped or mapped to themselves. It's not possible that, for instance, some vertex here is mapped to there and then vice versa, but the other are fixed. If there is a slight movement from one part to the other one, then it moves as a whole, and then the other one is put to there as well. So this explains the rightmost factor. Then this general linear group is just the automorphism group of the right-angled Artin group associated to a complete graph, so to a free abelian group of rank D. So this explains the whole set on the right. Now this factor or this free abelian factor in the beginning comes from transactions that are not coming from the other factors themselves. These transactions take one vertex in the clique and one vertex in the other part. And what they do, they transvect or map the vertex in the right-hand side with the element you chose from the clique. This works for any choice of vertex here and there. And all these transactions will in fact commute. This will generate a free abelian group. So this gives the whole automorphism group, and then the fact that there is a semi-direct product comes from that if you conjugate such a transaction with any of these type, you will again get a transaction, but it will be a little bit different. So it will still be a transaction, but it will not be the same as the one you started with. So this gives a description in another way. This is useful if you know these automorphisms to some extent, or have some properties, then it can be useful to have this type of decomposition to see if you can conclude something about the whole right-angled Artin group A gamma if you add some free abelian part to them. Okay, so this is how algebraic properties for automorphism groups are related to graph theoretical properties of your graph. And now we've done, I will not say the basic type, but we've done huge or major parts of the group theoretical aspects. And then we've investigated subgroups, we've investigated factorizations, and we investigated automorphism groups. And there is a last type of construction that is ubiquitous in group theory, namely quotient structures, or moving from one group to another one in a sort of natural way by factoring out certain elements. And on the level of graphs, this, if I may say so, could not be simpler. And there is a very natural way to move from one graph to another one. In fact, there are two. You can either delete vertices and corresponding edges, or you can just add edges on your graph. And these two types of constructions, so deleting vertices, have some analogous construction on the level of groups. So if you delete a vertex, this boils down to modding out the normal subgroup generated by this set of vertices. Then by getting a new graph, you would hope that the corresponding quotient group will be isomorphic to the right-angled Artin group of the resulting graph. And this is indeed the case. And the proof is starts with, you just take the natural homomorphism. So every vertex that remains is mapped to itself, and all vertices that you delete are mapped to the trivial element. And the kernel of this homomorphism will be, in fact, the subgroup or the normal subgroup generated by the vertices you delete. And in this way, you get a natural way of moving from one graph or one right-angled Artin group to another one by taking quotients. Another way is just by adding edges. And the same thing applies. If you take the natural homomorphism, so the inclusion, as you could say, from this graph into this one on the level of right-angled Artin groups, you get the corresponding quotient structure. Now, this deleting operation is especially useful because this gives a way of argumenting by induction on the number of vertices by taking quotients. You already had it on the level of subgroups, so this is also a nice property. Every induced subgraph will give rise to a right-angled Artin group that is both a subgroup and a quotient of the right-angled Artin group you started with. So here you see how you obtain it as a quotient, but you can also see it as a subgroup by the result by van der Leck, as we saw in the beginning. Okay, so with the deleting vertices, I went one step further. I don't want them to be normal. So these subgroups or these normal subgroups, I don't want to be merely normal subgroups. I wanted them to be characteristic. For purposes I will explain in the second talk. Now, if you recall, we had a generating set for our automorphism group, graph automorphisms, inversions, transactions, and partial conjugations. Now, since it is a normal subgroup, it will be closed under conjugation and under inversion. But it will not necessarily be closed under taking graph automorphisms of applying transactions. And this is what I wanted to solve. I want to see which groups of this or subgroups of this form, so which normal subgroups yield characteristic subgroups in this way. Now, the naive thing to do is, well, just make them characteristic at all vertices that could make it not characteristic and see if the group generated by these vertices is a characteristic one. This was what I did, and it appeared to work. Namely, so the construction in more detail, you start with a vertex V, you put it in a set V0, and then inductively you add all vertices that would give rise to a transaction. So you add in the ith plus one step all vertices W, such that for some vertex in the ith set, you would get this relation so that the map V prime maps to V prime times W is a well-defined transaction. In this way, you will add all vertices that give rise to transactions so that it will be in first instance closed under taking transactions, the resulting set. So we do this for all I, And then, so you take the union over all these i's to get one vertex set. Since your graph is finite, this process will end after a finite number of steps. So after this step, you would suspect that it's closed under transactions, and this will be indeed the case. But then you have to close it under graph automorphisms. And one way to do this is just apply all graph automorphisms on this v omega and take the union. Now, it could be that at this point, we will have to repeat the same operation with adding possible transactions, but it is not the case because this relation behaves well under applying automorphisms. So this will yield the characteristic closure of V, and as we'll see in a moment, this will indeed yield a characteristic subgroup. But I'll just illustrate the process I described here. So if you take this as a graph, and I start with the red vertex. So the blue one is the vertex in the link of the red one. So in the next step, we have to add all vertices that contain the blue vertex in its link. Now, there is this black one. Its neighbors are this one and this one. So it contains the blue one. We add this red one. So here, by symmetry, the one below is also one we have to add. And then this blue vertex itself contains this vertex in its star. So we also have to add this red vertex. Okay, so V1 equals the red set. And now we have to see if there are other vertices we have to add in this step. Now, the link of this red vertex consists of this blue one, but also of this red one. But there is no other vertex that contains these two as neighbors or as the vertex itself. So on this side, we don't have to add anything else. And then in the same thing on the other side, there is nothing else we can add by this operation, nor for the vertex here in the middle. So at this point, our V omega construction is already done. So at this point, it could be closed under transactions, but we have to apply graph automorphisms as well to fully close it under all automorphisms. And then there are only two other parts we have to add, namely by symmetry, the one here and above and the one here below. So applying this construction on this red vertex yields this subset of vertices as a characteristic closure. And then, as I said, the name giving is intentional. I proved together with my supervisor, Karel de Kimpe, that the subgroup N of V prime, so the normal closure of V prime, is characteristic if and only if your V prime is the union of all its characteristic closures of the vertices it contains. And this gives a very easy way, to some extent, of proving if a certain subset of vertices yields a characteristic subgroup, or finding ones if you just start with a vertex. So for instance, which subsets give rise to a characteristic subgroup? The subset, for instance, consisting of all vertices whose degree, so number of neighbors, is at least a given number k. Now, why will this be closed under this operation? Well, let me just give the idea. If you take two vertices v and w such that this relation holds, then the degree of w must be at least the degree of v. Why? If they're not connected, then this relation is simply link of v is contained in the link of w. So the number of neighbors of v has to be at least the number of neighbors of w. And if they are connected, then this transforms into the star of v, and you have the same argument you can apply. So from this step, the degree can only increase. So you only add vertices in this step with higher degree. And automorphisms of your graph preserve the degree. So if you apply an automorphism, the degree won't change. So you won't add any vertices of lower degree. So this one gives rise to a characteristic subgroup. For a specific choice of k, this will yield a very interesting one, but this I will talk about in the second talk. Okay, so this is to some extent the easy examples of, or the easy types of constructions or properties you can investigate on group level and how they come from graph theory, I want to end with a bit more involved example, namely the concept of lower central series of your group. So let me recall the algebra behind this. So given a group G, we define the lower central series as follows. The first term is simply the group itself, G. And then the next term is the commutator of the ith factor or the ith term with G itself. So for instance, the second element in this series is just the commutator subgroup, and then you repeat this process. So this chain of subgroups is called the lower central series of G. And for instance, this is used in the definition of nilpotent groups. If your group is nilpotent, if and only if your lower central series ends up in 1 at some finite index. And the nice thing about these lower central series is that, first of all, each of these groups is a normal subgroup in G. And by construction, is each of these factors an abelian group. So from our group G, we can construct lots of abelian factor groups, which give or could give lots of information about the group itself. But abelian groups are often much easier to work with than non-abelian groups. So this is one of the reasons why we look at this. And one of the types of questions that is often posed is, if you start with a finitely generated group, then all of these factor groups will be finitely generated abelian groups. And moreover, if you start with a torsion-free group, so no element has finite order, you would hope that this factor group will also be torsion-free. But this is unfortunately not the case. There are examples where your whole group G is torsion-free, but one of these factors has torsion. So one question is, for which groups are these quotients torsion-free? Because free abelian groups of finite rank are as close as you can get to vector spaces in group theory as you would like. So this is very useful to work with. And moreover, if they are torsion-free, they are free abelian of finite rank. So you can try to find a Z basis, so a basis as free abelian group. And then the question is, can we find nice basis, where nice can be anything you define to be nice. And for right-angled Artin groups, this has been intensively studied. It has been done for free groups and then generalized to right-angled Artin groups. So what I now will describe is a way of finding a basis for these factors, and it will also prove implicitly that the factors are indeed torsion-free. And the construction is due to Linden, who started with this, and then it was generalized or further investigated by other people, but I will give the names later on. So we start with our vertex set V, so V1 up to Vn, and we take all words on it. So just any concatenation of the letters you take, you want, these are the words. And then on this set of words, we'll put the lexicographic order. So the one you will find in a dictionary. So the empty word we denote by 1. This is the smallest element. 1 is strictly less than V1, strictly less than V2, and so on up until Vn. So we order our alphabet alphabetically. And then for words of longer length, we write them as one of our letters in our alphabet times another word. And then U is strictly less than W, if and only if the first letters are preceding one another. So if VI is strictly less than VJ, but if they are equal, then you move on to the next letter, as you would do in a dictionary. And with this lexicographical order, we can define Linden words in a recursive way. So the Linden words of length 1 are just your letters of your alphabet, V1 up until Vn. And then for length 2, you use the ones of length less than, or length 2 and 3 and so on, you use the one of smaller length. So all Linden words of length k are composed of Linden elements of strictly lesser length, such that x is strictly less than y. So you can't pick all Linden elements of lesser length and combine them, but they have to satisfy this relation. So as an example, for n equal to 3, length 1 we already had. For length 2, well, you take any two Linden elements or Linden words, sorry, of length 1, such that the first is strictly less than the second. Now, there are only three possibilities, v1 and v2, since v1 is strictly less than v2, also v1 and v3, and then v2 and v3. There is no Linden element of length, or Linden word, sorry, of length 3 that can start with the letter 3, since v3 is not less than any of the other Linden elements of length 1. Okay, so this gives all Linden words of length 2. And for length 3, you can repeat the same process. So let us start with first x equal to v1. Which Linden words of length 2 are strictly bigger than v1? Well, all of them. v1 is strictly less than v1 times v2, because, okay, the first character is the same, but then in the second place, we have v1 times 1 is strictly less than v1 times v2. So 1 is strictly less than v2, hence v1 is strictly less than v1 times v2. So this is a Linden word of length 3. And then similar arguments apply to the second and the third word. Then you repeat the same process starting with the letter v2. And you can't start with the letter v3 because, yeah, v3 is not strictly less than any of the other Linden words we had already. So at this point, we cannot start with a Linden word of length 1. So we move on to Linden words of length 2. So here we start with a Linden word v1, v2, and add the next smallest element, namely v2. And in this way, we continue. So with this construction, we will end up with, let me count, 8 Linden words. And this procedure up until now is independent of the graph. So I just took some vertex set v, but the graph will not come into play up until the next step. Because in the next step, and I had some tongue slips where I mentioned Linden elements, but this is different from Linden words. Why? So now Linden elements depend on the graph you are using. So if we take, for instance, the graph gamma to be this, so v2 and v3 are connected, and this is the only edge, then to construct Linden elements from Linden words, I have here the following intuitive approach. Namely, Linden elements are those Linden words that you cannot make larger in the lexicographical order by applying the commutating rules. What do I mean on that? For instance, v2, v3 was a Linden word, as we saw, but this is no Linden element. Since if you apply the commutating relation, we can swap v2 and v3 place. It will represent the same element in some sense, but this v3, v2 is strictly bigger than v2, v3. So we've made the Linden word v2, v3 bigger by swapping. So this is not a Linden element of our group. On the other hand, v1, v2 is, because we have no swapping relation we can use. v1 and v2 are not joined by an edge, so we cannot swap them. So v1, v2 will be a Linden element. And if you do the same reasoning for the other words, so the Linden elements of length 1 are simply your generators. This will always be the case. But the Linden elements of length 2 are precisely those that are not joined by an edge. So we see that v2, v3 is dropped from this list, but the other words of length 2 are also Linden elements. And then for length 3, you can apply the same reasoning. I won't go into detail here as to why it works. But for instance, if you take v1, v2, v3, so here you have v1, v3, v2, but if we swap v3 and v2, these words get smaller. So conversely, if we start with v1, v2, v3, by swapping 2 and 3, the words get bigger. So this explains why this Linden word is a Linden element, but the other one is not. Now, I should add that this is a quite informal and intuitive way of thinking about it. To make this rigorous and really well-defined, there is some more work you have to do, but I thought this was more appropriate to put in a presentation than going through all the details. Now, we have 2 steps. Linden words. Next step was Linden elements. Basis, or we want some basis for our factor groups. Now, in these factor groups, I've used commutator brackets. So in the next step, we will introduce a sort of bracketing way to make our Linden elements into basis elements of our factor groups, well, in the following way. So any Linden element of length at least 2 is the product of two smaller Linden elements, where the first one, x, is also strictly smaller than the second one, y. Now, there might be several factorizations. You can, perhaps not for length 3, but for longer lengths, there will be multiple possibilities to decompose your Linden element as a product of two other ones. And you choose the one where your second element, y, is minimal. So it's the smallest one in all possible factorizations that satisfy also this condition. This factorization is referred to as the standard factorization, as of w. And then with this standard factorization, we can inductively define a bracketing procedure. So the bracketing of w, if its standard decomposition is xy, is defined as the bracketing of x, comma, bracketing of y, and this put between new brackets. So, and then x and y are strictly shorter in length, so we can inductively work our way through the elements. So as an example, if you take v1, v1, v2 as Linden element, there is only one decomposition in other Linden elements, namely v1 and v1, v2. So the bracketing of this element is the bracketing of v1, which is simply v1, comma, the bracketing of v1, v2. Now, the decomposition of v1, v2 is just v1, comma, v2. There is nothing else you can do. So this gives the bracketing of v1, v2, and put together, we get the bracketing of the Linden word v1, v1, v2. And similar reasoning you can apply for the other Linden elements. So this gives us 5 Linden elements with a bracketing based on our graph. And then finally, the main result is that for any right-angled Artin group A gamma, and for any k, the kth factor of the lower central series, so gamma k modulo gamma k plus 1, is in fact a torsion-free abelian group, and it has a z basis consisting of bracketed Linden elements of length k. So the procedure I explained up until now gives us a z basis for each factor of this lower central series. Now, there is a bunch of names on top. So Droms, the same from the isomorphism theorem, but also Krop, Lalonde, Linden is the one who put his name on the letters, and there are several other names, all worked with on this construction. But I put one name at the end, so Richard Waite put in his PhD thesis and also in an article, all this information bundled in a rather nice way, in the sense that I used this reference when working on my master thesis for this topic. So that's why I put his name apart. It was the reference I used, but the other names, so Droms, Krop, and Lalonde, and other ones I did not mention, also worked on this. So the credit goes to the first people for finding it, but Richard Waite also did a very good job in writing it down so that it's clear and bundled together. So this result gives us a nice basis with which we can work to some extent if we want to say something about the factors of the lower central series. And as there is a star or an asterisk, I will use this in my second talk, or refer to this in my second talk. Now, on a other level, we have this basis, but to find the dimension, this is quite cumbersome work. And on another way, in a slightly more complicated way, there was a formula derived for the rank of your ith factor. So we know it's a free abelian group, but if you are interested in the rank, we can compute this as follows. And this is by Papadima and Suciu from 2006. So for a right-angled Artin group A gamma, we know this vector group is a free abelian group, so it has a rank Ri, finite rank, and then the Ri's are related in the following way. If we take this infinite product, so 1 minus t to the power I, and this element to the power Ri, then this infinite product will yield us exactly the clique polynomial of our graph gamma evaluated in minus t. Now, what is the clique polynomial? This is the polynomial that counts the number of cliques or induced subgraphs isomorphic to a complete graph of size I. So the coefficient in the polynomial expression of Pt with exponent I is the number of cliques of size I in your graph gamma. So this clique polynomial can be computed in finite time. This is only a finite number of coefficients, but with this finite number of coefficients, we've captured all the ranks there are in your factors of your lower central series. And in fact, this lower central series will have an infinite number of factors. So each Ri is in fact at least one. So the infinite number of information of the ranks is captured by a finite number of coefficients. So this is quite strong, that you can capture an infinite set of information by a finite set of elements. But the proof is quite involved and uses a quite strong results. And it doesn't give an idea of how the basis of a basis. So for working with a basis, you could use the result by Dromskrop et al. But if you are simply interested in the rank, you can use this result to compute it. Although deriving the Ri's from this relation is also not an easy task, but it gives some idea what you can do, or at least for the smaller values of I. Okay, then one last thing. To solve problems in group theory, one approach is to try and make it into a linear algebra problem. And this is one way of how you can do this. So you have these factors of your lower central series. There are abelian, and let's assume that there are 3 abelian of finite rank. Then you can put all of them together with an infinite direct sum. You call this L of G, and then we can put on this the structure of a graded Lie ring. So we put a Lie bracket on it. So we define it on each Li, and then extend it by linearity. So the Lie bracket of 2 elements x and y. So x lies in, or this coset lies in Li of G, and this coset lies in Lj of G. If we take the Lie bracket of these 2 elements, we define it as the commutator bracket of x and y, and we put it in Li plus j. So this defines a Lie bracket. And what do I mean by a Lie bracket? So it has to be such that if you take the Lie bracket of an element with itself, it yields 0. It has to be antisymmetric in its arguments. So the Lie bracket of x and y is the same as minus the Lie bracket of y and x. It has to satisfy this identity, and this is called the Jacobi identity. So these 3 axioms make it into a Lie ring, and the graded part means that this inclusion holds as well, but the latter part is just by definition of our Lie bracket. So this turns your Lie, this set Lg, into a Lie ring. So some vector space between quotation marks over Z, but you can easily make it a vector space over C by extending your scalars. And as we saw before, if you take a right-angled Artin group A gamma, the bracketed Lin elements will form a Z basis of this Lie ring. A Z basis as Z module, not necessarily as a Lie ring, so with the bracketing operation, but we have already a basis of this Lie ring. This as an aside. The main result I want to mention is this one, which is also due to Papadima and Suciu. And this is the last thing I would like to say for today. So as for groups and other things, you can define the presentation of a Lie-ring. So the presentation SR gives us the following ring. So you have a free Lie-ring over S in similar way as you have a free group on a generating set. And then you mod out by the ideal, so the Lie ideal generated by R. This gives us the notion of a presentation of a Lie-ring. And the nice result I would like to end with is that there is, in general, not a relation between the presentation of a group and the same presentation, but then interpreted as a presentation of Lie-rings. But for right-angled Artin groups, this is the case. So this presentation is exactly the same as the one for a right-angled Artin group. But if you interpret it as a presentation for a Lie-ring, you will get the associated Lie-ring of your right-angled Artin group. So although the same result does not hold for arbitrary groups, for right-angled Artin groups, this holds still. So with this, I would like to end, and I hope I've shown that in many cases, your right-angled Artin groups behave as you would like. But in many cases, also the proof is not that easy. Proving this also uses a lot of strong theory and other results. So it's highly non-trivial, but it's very nice and useful that this presentation holds in the case of right-angled Artin groups. And I can mention some other notions. So the same relations between graphs and groups has been studied for instance, Bierry, Neumann, and Strebel invariants and the cohomology of groups. There are other notions that I didn't touch or didn't mention, or I don't even know of, that also have been studied in this context. But I won't say anything about this anymore. Thank you very much for your attention. And if there are any questions, I will be happy to answer them.
Thank you, Peter. So I believe that there are questions, at least I have questions, but now, does anybody have questions before I start? I'm sure they have, but they feel shy. So Peter, in your talk, yeah, now it's difficult to ask questions up to my opinion, because this talk is a kind of a talk with the known results which can help you if you know graphs and don't know groups, or oppositely, if you know groups but don't know graphs. It's really like how to say it, a dictionary which connects graphs and groups, and yeah, nice. I am more specializing in groups. That's why I have a question about groups. So in this, somewhere in the middle, you introduced a way how to construct by a graph a characteristic subgroup of a group.
Yes.
You choose some vertices, and then there is an iterated procedure, and at the end it gives a characteristic subgroup. So in group theory, I know at least several characteristic subgroups, like a subgroup generated by powers, or a subgroup generated by commutators, or subgroups generated by, you know, by some words of some specific form. But here, going from graphs, I know only one procedure is exactly what you said. Do you know some other procedures to construct characteristic subgroups from graphs?
Short answer, no. Slightly longer answer, I've done it for vertices, and I've been wondering if you can do something similar for edges. So do the same thing, start with an edge and see what happens if you apply automorphisms. But as an edge consists of two elements, things can get ugly quite quickly. And I didn't see any use or direct use for a construction of this type when studying or researching for my master thesis. So I left it a bit on the background. Perhaps there is something in that case that can be done, like a similar construction that also yields characteristic subgroups of a different form, because if you start with, if you want to find characteristic subgroups generated by special subgroups, all of them will be of this form. This is due to the fact that we've proven it's an if and only if. So if you just use vertices, then you will not get anything else. Of course, if you want to see it for other starting points, powers of vertices, commutators of certain vertices, other words, then I have no idea. Other ways of finding characteristic subgroups based on the graph. I did some literature research back in the day when starting my research. I did not find any, but perhaps in the past 2 or 3 years there have been some new results. So I cannot give any more examples where I know that it yields characteristic subgroups. But as I said, perhaps if you do a similar construction starting from an edge, or I should say a non-edge, so 2 elements that are not connected by an edge, and apply the same procedure, perhaps you can get a characterization. But if I recall correctly, when I started doing it, it got ugly quite quickly. So I don't know. Feel free to try it out. I'm interested.
I'm not sure that I will try, but yeah, who knows? I have one more question about this result,
Sure.
about ranks of the quotients of the lower central series. There were lots of authors, and the date is 2015. I mean the top.
Yes. So I think the work of Droms, Krop, Lalonde, and all the other one is somewhere in the 80s, 90s, or beginning 2000s. So they started with free groups. There they introduced some construction. I think the name corresponding to this isn't even here. I think it's Magnus who did it. So he did it for free groups. Then some of people try to generate the construction to right-angled Artin groups, so the graph groups, I think they will call them graph groups, and try to see if you can do a similar way. But as far as I can see based on the literature, this was like several partial results, in the sense that one person did the whole construction for Linden elements and Linden words, but did not make the step to see it as the basis or something like that. And Richard Waite combined them in one work, so in his PhD thesis, and then also published this part as a paper, where you have the full procedure described here. He starts with Linden words, introduces Linden elements, formalizes this, and gives us the theory why it works. Then proves that it is indeed forming a basis, that all the factors are torsion free. So he proves everything in one result, in one paper. This read a bit more easy than reading 4 or 5 different papers. Also, there are older, so the writing style is a bit different than current mathematics. So this is why I put the names like this. So Richard Waite is more of a reference, as in combine all the results. The true finding of the results is due to the first people I mentioned here.
I see. Thank you. Yeah, that was the reason for my question. I know only one result of Magnus about free groups, and he gave an explicit, wonderful formula of the number of generators, and I see that this generalizes this, and that's why
the necklace polynomials, or this summation over the divisors of n in the Möbius function. Well, yes,
something
this you can derive it in a similar way from this relation. Yeah, indeed.
So if there are no more questions, we're grateful to you. We thank you and waiting for applications of all of this.
Well, one application.
Okay. See you on 30th of November.
Indeed. See you.
Yeah, in 2 weeks.
Yeah. Okay.
Okay. Thank you very much for the lecture.
Yeah,
great. Yeah. Thank you.
It was a pleasure. Okay. Bye. See you in 2 weeks. Have a nice evening.
See you in 2 weeks. Yeah. You too. Bye.